Hello and welcome to my poster presentation. My name is Nick Sajjadi. This presentation is entitled Medical Student Academic Performance is Not Normally Distributed, a Statistical Analysis for Future Analyses. And this work was done in collaboration with Kaylee Bixler and Dr. Joseph Price. In most academic fields, student mastery is typically assessed using examinations, either in written or practical format. And it's often assumed that the distribution of scores approximates the normal distribution or the bell curve. And while this notion has been debated, the assumption of normality has important consequences in statistical analysis. Many tools used to characterize datasets rely on the assumption of normality for accurate conclusions, for drawing accurate conclusions. And if datasets are not normally distributed, then corrections can be made or other tools can be used to account for this, allowing for more meaningful analysis. So investigators seeking to study academic performance at OSU's College of Osteopathic Medicine need to know whether the exam sets are normally distributed so that the most appropriate inferential statistical methods can be selected. Thus, we sought to ascertain the normality of exam score distributions for first and second year medical students and to determine exactly how normal or non-normal the distributions are. Findings from this study will be useful for future investigations wishing to perform further analysis of academic performance at the College of Osteopathic Medicine. So 58 exam datasets from the classes of 2022 and 2023 were de-identified and assessed using R and RStudio with the foundational package Tidyverse. So first we determined the normality, which is typically ascertained two ways, graphically and numerically. So for the graphical exploration, we utilize QQ plots, which take your dataset and calculate the mean and standard deviation, and then make a theoretical dataset that is normally distributed using the same parameters, which you can then compare to your actual dataset. For the numerical analysis, we use the Shapiro-Wilk normality test, which has a null hypothesis of normality. Thus, any p-value less than 0.05 corresponds to statistically significant deviations from normality. And due to the problem arising from multiplicity, we corrected the resulting p-values using the Benjamini-Hochberg procedure. Then we used the package desk tools and applied the SAS method to characterize the deviations from normality by determining skewness and kurtosis. Skewness is deviation from normality due to outliers, and kurtosis is deviation from normality due to variance, and we did this for each exam. So here's our results. The QQ plots, again, generate a theoretically normal distribution, which is displayed as a straight line and surrounded by a shaded area, which represents a 95% confidence interval. The points on the graph represent actual student scores on any given exam. And the granularity here isn't great, but you can make out that most exams had points falling off of the theoretical normal line and often outside of the 95% confidence intervals, indicating statistically significant deviations from normality. Likewise, the numerical analysis revealed that 53 out of 58 exams, or about 91%, had statistically significant deviations from normality. The table here is just reporting those values for each exam and is mostly featured just for the completeness sake. So here's the results for skewness and kurtosis. By definition, normal curves have a skewness of 0 and a kurtosis of 3. So skewness within plus or minus 0.5 are considered minimally skewed, and data sets that have a skewness with values between plus or minus 0.5 and plus or minus 1 are considered moderately skewed, and data sets with skewness values over plus or minus 1 are then considered highly skewed. Negative values will means that your distribution is skewed to the right, leaving a long left tail, and a positive value means that the curve is pushed to the left. So 43 out of 58 exams, or 74% of the exams, were moderately to highly skewed, with an average skewness of minus 9.5 or 0.95, a median skewness of minus 0.7, and a standard deviation of 0.94. So with kurtosis, we take the excess kurtosis, which is kurtosis minus 3, which tells you how peaked or flat a curve is. A normal curve would have an excess kurtosis of 0, because its kurtosis is 3, so 3 minus 3 is 0. If you have a positive value, that indicates a leptokurtotic curve, which means that the curve is centrally peaked. And a negative value would mean that the curves are platykurtotic or centrally flattened. and again, a normal curve would be mesokurtotic. So 89.7%, or 52 out of 58 exams, were platykurtotic. None were mesokurtotic. The average excess kurtosis was minus 0.65, the median was minus 2.7, and the standard deviation was 7.22. And you can see this here, categorized as these, for the skewness, the blue and green dots would be highly and moderately skewed respectively, and then here you can see we're drawing a line at 0, and anything less than that is going to be platykurtotic, which was most exams. Here's the same information, just sort of in a summary, a histogram here. So what does this mean? Taken together, our results suggest that on average, exam score distributions are skewed significantly to the right and flattened about the peak, which means that which leaves a long left tail. And this may mean that there are many high scores, and or that there are consistently a subset of scores far below the class average. Additionally, the paucity of normally distributed exams may suggest that the assumption of normality regarding student performance is inappropriate in this context, and that methods curving exam scores to normality would also be inappropriate. Lastly, inferential statistical analysis on these classes should use tools suited for non-normally distributed data to avoid inaccurate conclusions, as the majority of the exams are not normally distributed. In conclusion, we recommend continually collecting these data for each class and performing this analysis first before any other inferential statistics are used. And we also believe that it's worthwhile to investigate the causes and repercussions of the negatively skewed platykurtotic distributions, because knowing this may allow for optimizing course design, exam design, and student performance, leading to better educational outcomes. Here are our references. And I just want to thank you for your time. Please feel free to contact me with any questions regarding this project. Thank you again.